So we're going to start by suggesting that the mass was pulled outwards this distance. This will be our initial displacement, x naught, also known as the amplitude. And this is going to represent time equals 0. Now, at this moment, we have just released the object. So at this moment, v equals 0 as well. But we are at the amplitude. So this will be the maximum displacement of the object. There are 3 principal things we're going to trace. First, we're going to trace velocity, we're going to trace force, we're going to trace energy. But we're going to look at all of these things and when they happen. So at this instant, the kinetic energy is 0. And all the energy is in elastic potential, which is at its max, 1/2 k x naught squared. At the same time, we are at maximum displacement, which means we are also experiencing the maximum force on the system. There's a consequence here that when you're at maximum displacement, you're experiencing maximum force, you're also experiencing the max acceleration. If you've ever been on a ride that tends to whip you back and forth, this is when you feel like you're kind of being flung back or flung forward, because this is where the acceleration is at its maximum. Advance a few moments into the motion. So we are no longer at t equals 0. We're going down one step. Now, this is an intermediate position. We're displaced some value that is less than x naught. This is not a specific moment in time. However, at this moment, v is no longer 0. And a is no longer at a maximum. We still have a force in this direction. And that force is based on x. So whatever x is what the force is now. But we also now have a velocity in this direction. This is an intermediate position. I say that because the energy is mixed. There's both kinetic energy and elastic potential energy. And if we didn't do it in this class, you should prove that this equals the maximum. Did we do that in here yesterday? We plugged it in. So we know that this has to equal 1/2 k x naught squared. So we have a mix of energy between the two, but it can't exceed the maximum amount of energy. So let's advance this a little bit. The next position I want to talk about is at equilibrium. Now, here's where these are subtle things, but they ask this kind of stuff a lot. We are 1/4 of the way through an oscillation. 1/4 of a way. This entire worksheet pictures only half of an oscillation. I don't need to give you the whole oscillation. That's a little waste of time. But it pictures half of an oscillation. That's important because that means right now t is equal to 1/4 the period. It is very common to show a block hitting a spring and being brought to rest on the AP exam and them asking you how long did it take for the block to be stopped. And people spending an incredible amount of time trying to figure that out when it's just 1/4 of the period. There's no motion equation that they can really work out there unless they try and use one of the sine or cosine function equations to get the time. It's hard. It's just 1/4 of the period. People miss that. They miss that that's the simple harmonic motion question that they've snuck into the problem. So understand, if a box hits a spring and it only goes a quarter of an oscillation, then it's a quarter of the period. That's how long it takes. There's several things to know about at this moment. First, there is no elastic potential energy. This is because x equals 0. We are at equilibrium. That means that all of the energy is in the form of kinetic. So we are at 1/2 mv max squared. And you have an expression for V max based on K, X naught, and M. Also, at this moment, the force is 0 and the acceleration is 0. So although we are at maximum velocity, there's no force acting on the system at this instant. Now, throughout this entire discussion, this description so far, from our initial release of the object to our point where we're at equilibrium, the force and the velocity have been in the opposite direction of the displacement. Don't throw that away. Keep that close. Direction is important here. During this next portion of the motion, I need to advance this upwards a little bit. Looks like my equilibrium line didn't extend all the way down the page. So there we go. Now, the object has passed equilibrium, still has a velocity this direction. No longer at a max. Because now the force has changed direction. We are on the other side of equilibrium. Displacement has now become negative. It's on the left side of equilibrium. So the force has become positive, which also means the acceleration is now also pointing in the opposite direction. It shouldn't be a big surprise. We're slowing the object down now. So although the object is still sliding to the left, the force and acceleration has changed direction. So while it was speeding it up in the beginning, now it's beginning to slow it down. We still have a mixture of energy, 1/2 mv squared plus 1/2 kx squared. And this still has to equal 1/2 kx naught squared. Still equals the maximum amount of kinetic energy. Now, we are somewhere between 1/4 t and 1/2 t. We're somewhere between a quarter of the period and a half of the period. But at this moment, nothing is 0. But eventually, we're going to make it to another place where v equals 0. The object stops. This means we have a whole slew of things that are now maxed again. The force is at a maximum. The acceleration is at a maximum. Velocity is 0, but we are now at a negative amplitude. All of the energy is in the form of elastic potential. And the time is 1/2 of the period. Now, the system's going to restart itself. It's going to start going the other direction. And when it begins to go the other direction, of course, this whole thing repeats. Suddenly, the velocity is going to start being in the same direction as both the force and the acceleration. That will occur until we make it back to equilibrium. And we'll pass equilibrium, and we'll make it back to our starting point. I don't believe I have to repeat this. I think just half of this is enough. But what I want to impress upon you is every oscillator has this kind of interplay between displacement and velocity. But they don't all measure their displacement the same way, nor do they measure their velocity the same way. But they all have this interplay. Moreover, there is a certain amount of contextualization. This is a spring mass oscillator. If you turn this so that it's vertical, this system is different. In the vertical version of this system, you have a constant downward force acting on the system. That changes the nature of how the system behaves, because under those circumstances, the equilibrium position is a little bit unusual. And where is equilibrium when you make this vertical? Or when the force is equal to 0. The definition of equilibrium is a little bit more elusive there. So it's important to understand that we're using this as our model for each system. So what I want to do today is I want to talk to you about the first and most likely model you should come to expect and how it relates to this model. Having this sheet's helpful, and it should be helpful mostly about the nature of the energy in the system and the timing of the system. But also for all of you people who did not have AP Physics 1, the people in C already knew this, or were supposed to. So they kind of had it tucked away. They've been through this a little bit. Leave this aside, you're going to want this. How the ideal system, the spring mass system, can be applied to any oscillatory system. And I usually don't get a chance to go into this, but we're in a position where we can today, and I really want you to have this understanding. What I want you to understand is that if we can figure out how our system is related to Hooke's law, then we can take everything that's about our simple harmonic motion system and apply it to the system we're studying. And so we're going to study a system that we already looked at. We're going to study the simple pendulum. Now, there is a problem with studying the simple pendulum, and that is that a simple pendulum is not a simple harmonic oscillator, but it's the most common approximation of a simple harmonic oscillator, so we study it. There are several factors about a simple pendulum that you should know. A simple pendulum is an ideal system, not a real system. There are no simple pendulums in the world. There are approximations of simple pendulums. A simple pendulum is not a weight on a string. Strings are flexible, they bend, and they stretch. So they generally say that a simple pendulum is on a massless rod that is inflexible and cannot bend, and that we have a point mass at the end of that string. So we'll start by identifying characteristics. The rod has a length of L. The bob, as it's called, has a mass of M. And it appears in my system that we are beginning at some position. I'm not going to use max because it's too much to write. I'm going to just put theta naught, some initial displacement. Now, we're going to have to come to grips with something. Hooke's law is about a displacement in meters, but we tend to look at pendulums by their angle. So we will have to realize that if we want to apply Hooke's law, we want to see if there's a way to express the forces acting on this system in such a way that we get a constant times a displacement. Now, to do that, we need to find a way of measuring the displacement of our pendulum, not in terms of the angle directly or the angle only, but in terms that give us a value in meters. Now, this part's not terrible, but I think some of you would think one of the best ways to measure it would be this way, which would be pretty easy to do. And L sine theta would give it to us. So we could say that this, if this were our displacement, we could measure it in meters by doing L sine theta. But is that the actual path that the pendulum will travel along and going back to equilibrium? We know it's not. The actual path is going to be like this, an arc length. What is this arc length? No. I want it in terms that are on the board currently. You guys are making this way harder than it needs to be. Yes, sir? Nope. You're thinking of the height. Yes, sir?
Theta over 2 pi.
Stop at the 2 pi's, guys. We just measure theta in radians. It's L theta. Delta x equals delta theta times r, right? I hope that looks familiar. We had a whole unit on rotational kinematics, and this would be the connection between a rotational value and a linear value. You're very tuned to pre-calc and degrees and having to make that conversion. You don't have to worry about this here. When you're given a value that is not expressed in units, like m or L or theta, it's any units that are convenient to your relationship. There's no need to just assume it's going to be in degrees or hertz or whatever. Make it something that's useful for your application. So here, I'll just say thetas and radians. And I can express the arc length as theta L. Here's the problem. We need to come up with whether our force acting on our mass looks like this. So we need to find a way to do that. Now, how many forces are acting on this mass? There are 2. So if you draw a free body diagram for the forces acting on the mass, you should have a downward force and a force of tension. Yes? Let's not add drag today. Do you really want to do that? This will be enough. Now, both of these forces contribute to causing this object to oscillate, both of them. So you have to decide an appropriate coordinate system in which to observe these forces. Now, you can choose a coordinate system that's aligned with the weight, but that would assume that the object is traveling along the red line. Or you can choose a coordinate system that's aligned with the tension, and that will assume that the object's traveling along the yellow curve. I'm going to suggest that we do the one that's aligned with the yellow curve. So I'm going to tap in a coordinate system. Like so. I'm going to take the off-axis force and break it up into its components. And recognize there's a component this way. And that component is mg cosine theta. And I see a component this way, which is mg sine theta. Everybody follow so far? No problems? Good, because net force equals MA. I'd like to see if I can't create something that looks a lot like our forces so that we get a differential equation. I want this to look like this. Now, it's not too hard right now. There's only one force in the direction of motion, and it's mg sine theta. That equals MA. But I can't resolve this yet. First thing I want to point out is that my acceleration is back towards equilibrium. This is going to be hard. I don't really have a point of access for direction, but I'm going to see if I can encourage you to see things the way I see them. The angle is this way, would you agree that my net force is in the opposing direction? It opposes the direction of theta. Even though theta is buried in the sine, I could put a little theta hat there if I wanted to indicate that it's opposing the direction of theta. The problem is that I don't want this to look like something times sine of theta. I want this to look like a constant times a distance. So I'd like to write this in terms of a distance, and I can write sine theta in terms of a distance. I mean, looking at my picture, sine theta is going to be whatever this is, x over L. Right? I'm just labeling this x. I know you're wondering why I would do that. Well, it's simple. If I do that, I get mg x over L equals ma. If I collect the constants, I get minus mg over L times x equals ma. And this looks a lot like a constant times a displacement. Wouldn't you agree? There's a problem with this, though. Our actual object doesn't travel along x. It travels along s, the arc length. The question is, are these two things equal? X is L sine theta. S is L times theta. This brings up the small angle theorem. It's not a theorem, but I don't know why they even say the word theorem in your textbook, which bugs me. It should be called the small angle approximation. For those, how many of you have heard about the small angle approximation? Not enough of you. So we need and if this is true, this is a decent approximation. And here's the important thing, what I was trying to get to all along. If that's true, then omega being the square root of k over m can be rewritten for a pendulum as the square root of whatever this is for k. Now, you'll notice the m's cancel here, and we get that omega for a pendulum is the square root of g over L. This means that every formula we just had for our simple harmonic oscillator now works for a pendulum too. You just plug this in anywhere you had omega. And all those motion equations, Vmax, all of that works exactly the same. A little caveat though, that's H. And H is L times 1 minus cosine theta. What you should really consider looking at is, what does this look like? So we're going to do this really fast. Make sure your calculators are ready. I'm going to do this way. All right, 1, 2, 3, 4. I have 1, 2, 3, 4, 5, 6. All right, so we're just going to do this fast. Left side of the room, you're in charge of converting the angle to degree, from degrees to radians. Everybody understand? So you're taking 1, 2, 5, 10, 30, and 40 degrees and converting them to the value in radians. Right side of the room, I guess left and right's weird for you guys. That side of the room, you're computing the sine of all those angles. In a few seconds, quite literally, I'm going to call these out, and you need to tell me what the numbers are to 4 decimal places each. The first time I get a pause, I blame that side of the room, and you get canceled. Quickly. Gotta hurry, it's almost club time. All right, 1 degree in radians. 0.0 what? Is it 0.159 or 0.0159? Thank you. Maybe. Oh, jeez, Mr. Sheldon. I'm the weak link. All right, sine of 1 degree. Sine of 1 degree. 0.0175. Okay, so whoever told me the conversion to 1 degree to radians did it wrong.
0.0175.
David was so adamant. 1745. Thank you. 2 degrees to radians.
Thank you, staff and students. At this time, staff, please release anyone who has a yellow club pass at this time. Only students that have a yellow club pass.
You'll be able to leave after this is done, after that failure. 2 degrees converted to radians is?
0.03491.
And the sine of 2 degrees. 5 degrees converted to radians.
0.0872.
Sine of 5 degrees. The same. All right. 10 degrees converted to radians.
0.1745.
Sine of 10 degrees.
0.1736.
And 30 degrees converted to radians.
0.5236.
And we know sine of 30 is 0.5. And 40 degrees converted to radians.
0.6981.
Sine of 40 degrees.
0.642.
So the question is, can we say that theta equals sine theta? If we can, so at the start yesterday, or 2 days ago, I pointed out that we're dealing with a Hooke's law restoring force. That's where the start was. My expectation is you understand that this, by simple application of Newton's second law, created this. Right? And then this became a super important and meaningful piece of information that showed up everywhere else. We had motion equations that contain it inside a function. And there's a range of these, and I'm not expecting you to have them memorized. I'm expecting that if I gave you one of them, you could tell me the other two. So a generation of motion equations. all based on a guess that we made about how to solve a specific type of second order differential equation. All of it controlled by this square root of k over m function, which I believe even in this class, I said we have, in most cases, replaced with omega to make it easier to write these out. Did I talk about that yesterday in here? No. Well, you won't like that, but it is the truth. There's a good reason why they replace it with omega. One of them is that inside the cosine and sine function, having a Greek letter like this, omega, has other meanings. The unit circle is supposed to actually show you this using omega as the angle, but they tend to show you theta instead. But there's another reason why omega is used here. Who can tell me what the unit of k is? That was a yes or a no. First on the draw, but not with the answer. You can figure it out by just looking at this law. X has to be in meters, F has to be in newtons. What must K have to be? Gabby? Newtons over meters. So inside here is newtons per meter per kilogram, all under the radical. Now, what is a newton? So that's kilograms, meters per meter second squared divided by kilograms, all under the radical. I think we can cancel some things out, don't you? By kilograms, by meters, and I'm left with, under the radical, the square root of nothing over seconds squared, which suggests nothing over seconds. If units cancel out, what unit are we likely to be in? Not hertz. This is a radian. There's a reason why it has to be radians and not hertz specifically. This is why I want to bring this up. Inside here, you can only take the cosine or sine of an angle measurement. And in whole numbers, angle measurements are in radians. Inside there has to be a value in radians. So this is to prove to you that omega is not a bad idea for a symbol here. It has to be radians per second. And this is called the angular frequency. Not a harmonic frequency, which would be in oscillations per second, but an angular frequency, which is in radians per second. And it is controlling how fast the system oscillates. So it is not uncommon for all of the things that we have listed here to be put in terms of omega and not square root of k over m, because that makes it generic to any oscillator. So all of this. Written as omega here, omega there, and omega squared there, which means A max is x naught omega squared, V max is x naught omega, period is 2 pi divided by omega, and frequency is omega divided by 2 pi. So this is the basics of all harmonic motion. It can tell you almost everything about a harmonic system. The only thing left out, and left out on purpose, is energy. Different systems have different forms of energy. And yesterday we were beginning to look at the energy towards the end of class. But these are the basic principal pieces of harmonic motion. Any question about that? There will be, because today we're going to talk about other harmonic systems. But before we do, again, I want to use this as our kind of our stepping off point to talk a little bit about what's and look for just a minute. Notice that the velocity has an explicit negative sign in the formula, which meant that starting at t equals 0, although the velocity started at 0, the moment we were no longer at t equals 0, the velocity was negative because our displacement was positive. Our object starts with a velocity opposing the displacement of the object. That's explicit in the motion equation. But also, it's explicit other places too. This is why the acceleration and the net force are both negative compared to the displacement. That's only true for the first quarter of motion. And then things start to change.